like to thank everybody for coming to our session. Thanks especially to anybody who said, yes, I might attend. Got us room size number 2, tied for 2. I think we're getting very close.
I think we are.
All right, without further ado, I'll present Dr. James Shanahan, who's acting data science, chief data scientist at NativeX.
All right. Can you hear me okay? I'm not sure if this mic is for posterity or for the audience here. How about now? Is that better? I'm not sure if it's... Is this better? Not really. Okay. It's on for sure, but I'll like to... Let me... All right. My name is Jimmy Shanahan, and today we're going to tell you about how data science is being leveraged within online advertising. And it's a team effort here, and I'll introduce the team shortly. So basically, this company called NativeX, I'm not sure if you've ever heard of them. They're a local company, and they were formerly known as W3I. And we're going to tell you how data science is being used to further optimize the consumer experience, the advertiser experience, and the publisher experience within the online advertising world of mobile apps. So, sorry, that's... So basically, we wanted to generate some interest by saying that NativeX is looking at data science and embracing it currently to optimize advertising in the mobile context. And we wanted to tell you about our experience so far. And ultimately, what we want to do is really increase user satisfaction, increase profitability for publishers, and also increase return on investment from an advertiser's perspective. And we want to tell you about some of the lessons we've learned on the way here in adopting data science and how we got started and where we are right now. So, in true startup fashion, this presentation came together last night. And we're going to do it live, just like Bill O'Reilly. So, when we started looking at data science initially, the problem that the execs at W3I and NativeX faced was, well, there were huge opportunities and there was a lot of instinct that was being embraced, and they thought that that led to profitability. But they also noticed that, well, Quark, this guy from Star Trek, I don't know if you recognize this guy, he may not be right, and hopefully by the end of the presentation we'll have convinced you that he's not exactly right. So basically, our hero is this guy here, Han Solo. So this guy basically states that without precise calculations, we'd be in big trouble. And we're going to try to convince you that Han Solo is the type of guy that you should be hiring if you want to embrace data science. So what is NativeX? So basically, NativeX is a mobile advertising network as well as a desktop advertising network. And so far, the idea here is to take offers or ads for other apps or other third parties and show them within the context of mobile apps. And the problem here is that we've got hundreds, thousands of potential ads or offers we could show. And the idea here is, which one do we show to a consumer at a particular context or time? And the goal again here is to increase the return on investment from an advertiser's perspective, because they're investing money in showing ads. And then also to monetize apps from a publisher perspective, because programmers, app developers, they also need to get paid. And in addition, we want to make sure the users are happy and engaged. So in terms of data, there are over 500 million devices which go through the NativeX network, or have gone through the NativeX network. And there are about 10 million daily active users. And this leads to the generation of over 100 gig of data per week. So that's quite a lot of data that needs to be organized and leveraged. So just to introduce the team, we got Brett over here, and Brett is an engineer and who loves math, and that's really awesome. Then we've got SA. He's more coming from the business intelligence side of things, and again, these are important skills for us to embrace because he's got a lot of core knowledge about data and also about the domain. And then we've got Joe over here, who's our core engineer, infrastructure engineer. And myself, I'm more of a scientist. So basically, today's presentation is not about science, really. It's more about how to engineer science to make it work in the context of mobile advertising. So just in case you're wondering how do we define data science. So for us, data science is about this kind of marriage of three different disciplines. Sorry. We want basically be able to hack up code and build systems, engineer systems. So we need a certain level of computer science competency. In addition, we need a lot of math because it's all about optimization. And here we're embracing techniques from statistics, optimization theory, social networks analytics, geo-informational spaces, and so on. In addition, we need some domain expertise and understanding how consumers behave in an app context. We also want to understand the marketing context and the advertising perspective as well. So in addition to these skills, we think it's also very important to be able to communicate. We need to be able to communicate what we're doing. Sorry, this is effectively to other engineers, other teams within the company, and then more especially to the executives as well. So a data scientist needs to possess potentially all of these skill sets. And if they are, then they're true rock stars in the data science sense. So one of our mantras at NativeX is that if we can't measure it, we shouldn't do it. And that's been instilled from the top down. And it's very important that when we start out a project, we need to have some metrics that we can measure success by. And we'd like to have objective measures of success. And we'll tell you more about those as we go through the presentation. Now, when it comes to science, there are certain methods and principles you can follow and be successful. And we endeavor to insist on rigor and try to avoid listening to the loudest voice or to the hippo principle, the highest paid person's opinion. And sometimes it happens that the hippo dominates the conversations in various organizations. But at NativeX, we're all about trying to be purely scientific in our rigor, where we observe certain behaviors, we formulate hypotheses, and then we try to model or test those hypotheses and establish some basic theories. And we try to avoid this actual method where we try to retrofit models or hypotheses to data to make ourselves feel good. Yeah. So NativeX has been in this business of mobile advertising for the last 3 years, and it has embraced data science quite a bit so far. And about a year ago, they decided to step up the game a little bit and say, okay, well, how do we bring state-of-the-art techniques to bear on all the data they had collected about consumer behavior within the app world? And so to get started, they looked at potentially buying a system or licensing a system to do this predictive analytics from a data science perspective. In addition, they said, okay, well, what are the alternatives? Could we find some expertise and hire them or partner with them? And so what happened is that they found me, and we've been building a team over the last 6 to 9 months to tackle these types of problems. And so we're going to walk you through the process that we follow currently. So we have the 6-step process to modeling at NativeX. And so the first step is to understand the problem domain. And then we selected a whole bunch of problems and we scoped those problems out. And then we tried to select a problem that was that had reasonably low-hanging fruit and that was going to bring big bang for buck quickly. So next step up is we needed to collect requirements because we have lots of systems, lots of teams, and we need to cater to all their needs. And in addition to collecting requirements, we needed to collect data. We needed to instrument various aspects of the advertising ecosystem and collect that data. And next step up is feature engineering. We needed to build various features or attributes of consumers, of apps, of advertisers, and explore the data as well. So these are all critical steps that we needed to get in place before we could start modeling the data and extracting patterns or various models such as linear regression models or Bayesian statistical models. And next in the pipeline here was we wanted to interpret and evaluate how good our models are. And we got various metrics for assessing the quality of those models. And finally, the ultimate test is putting the models that we learned from the data into the wild and doing A/B testing. So we're going to walk you through these steps here from an engineering perspective. And we're going to start with Brett, and he's going to tell us some little things about Bayes and metrics. So, Brett.
Go ahead and hit up the next slide. All right, so that's Thomas Bayes. He lived in the 1700s. He came up with this math formula there. I'm going to help walk you through it. It's one way that we can generate probabilities out of our data. And probabilities are good because it tells us how likely the user is to benefit from the offer that the advertiser is putting forward. It tells us how likely the advertiser is to actually achieve a conversion. And if both of those things happen, then the publisher, the app developer, gets to get paid as well. So everybody wins if we have our posterior probability correct. Let's go ahead and hit the next slide, essay. So the notation here is you got this vertical pipe. And that means given, basically. So P means probability. What is the probability of an advertiser converting given the advertisement request coming from a certain publisher? That happens to be equal to the probability of the publisher conversion given the advertiser times the probability of the advertiser irrespective of publishers and the probability of conversion on the publisher app irrespective of the advertiser. Go ahead and hit next. And I'm just going to go through all that again. We start with a white blank slate, a universe of possibilities. In this case, the possibilities are we'll either get a conversion or we won't per ad impression or view. So go ahead and hit next. So there it is. You have maybe roughly 1/8, maybe not even an eighth, maybe 1/9 of a possibility that this advertiser, irrespective of publisher, is going to convert on any device we throw it at, any publisher app, any time of day, any country. Yeah, thank you. So now here's same thing, but this is coming from a publisher's perspective. So we have a publisher app, maybe it's Temple Run, and Temple Run has a certain probability of leading to a conversion for an advertiser. Who knows which one it might be? It's going to be several. What we want to do is figure out where is the joint probability between the advertiser and the publisher. So go ahead and hit next. We start off with, so we've taken away the universe of all probabilities. We're looking at just the advertiser now. And there's a small corner where they overlap. So that's where we get, in the theorem up top there, the probability of the publisher converting given that the advertiser is advertiser A. So that's maybe 1/9. Okay. Come back. That's fine. Yeah, that's fine. Go forward. So how do we get just that one little dot? That is, go ahead forward. That is a fraction of a fraction. So the advertiser possibility of converting is 1/9. Inside that, it's maybe 1/10. So it's 1/10 times 1/9. And we get Go ahead forward. The intersection of advertiser and publisher against the universe of all possibilities. From there, we're still working towards the left-hand side of the equation. We've got the top row now, the numerator. Go ahead, hit next. So we multiplied to get there, and now we're going to divide the intersection into area B, and then we'll have a posterior probability of how likely advertiser A is to lead to a conversion on publisher at B. So that's one way of generating the probabilities from our data. Go ahead and hit next. Now, if Bayes were alive today, he would probably be familiar with structured query language, and he would have saved himself some effort. We're just going to take the sum of the conversions, sum of the impressions, filter by advertiser A and publisher B. We want a more general approach, so next. We want to know what the likelihood is for, I should say, the posterior probability that advertiser A is likely to lead to conversion against any publisher that we haven't run it against. Then we can start ranking the ads against each other in the context of a given user session. Once we have that information, go ahead and hit next. Okay.
Valuation.
Okay, so next I'm going to talk about evaluation. I've got a little bit of a demo. It's nice to have theories, and theories can be true. But in theory and practice are the same. In practice, theory and practice are different. So we need to test the models that we generate, and I'm going to show you how to do that, or one way of doing it. So I'm going to show you what's called ROC curves, receiver operator characteristic. Let me go to.
Not live. It is drag it across.
Oh yeah, let me make sure you guys can see this. There we go. So I'm going to import a library called ROCR. It's Rocker. The ROC stands for receiver operator characteristic. Bam, we've got the library loaded. And I will save a little bit of pain by copying and pasting. Let's get this guy. So we get a curve or a squiggle. What's happening here is across the vertical axis, we get a true positive rate. Across the bottom axis, we get a false positive rate. So we have these probabilities we've generated for the apps in the context of a publisher. It's not always right. So what we do is we take some set of data, say maybe 6 months of data, and then we save a week of data that is not included in our probabilities. And we play our probabilities against that week of reserved test data. So, and we withhold the information from the model. We say, we're not going to tell you which ones convert. When we generate the model, it knows which ones convert. When we test the model, it doesn't know which ones convert. So sometimes it says, I've seen this combination before. This guy is definitely going to convert. Wah, doesn't happen. We get false positive. But then the next guy comes in and says, okay, I'm maybe a little less confident this time, but I think this one's gonna go. So this is my next highest guess, and yes, it goes up. And let me show you the data we're using. It's extremely simple here. Basically, we've got these ordered probabilities. I just say 0.9, 0.8, 0.7. And then I've got 4 zeros and 3 ones. So if that's not intuitive enough, and it wasn't for me my first time, I have an Excel spreadsheet which will hopefully shed a little bit of light on how that works. And then I'll change the numbers up and show you how that works as well, so you kind of get a feel of what the different things do. And I assumed I would have more screen real estate than this. Let's go Control A and shrink down the font size. And resize our columns. Cool. So on the left-hand side, we have the prediction. For this combination, I'm extremely confident, 0.9, that it's going to convert. Actual, yeah, we converted. So far, we've seen 0 zeros, and we've just added 1 1. And by the way, I should also add, across the entire test data, after we've played the test data against the model, see how it did, we know how many actual zeros there were, how many actual ones there were. And so we say now we have 0 zeros and 1 1. So we're going to divide that into the total here. These are cumulative sums of the number of things we've encountered so far. Kind of what we're doing is we're drawing a line under row 2 there that says if everything below here were false and everything above here were true, what would your true positive ratio be and your false positive ratio be? Thank you for the live edit. Go ahead and double click the just to the right of the F there.
It is.
That's fine. You can expand the column out.
Oh, sorry.
Let's go back to the sheet. Okay, so we have achieved 1/3, thank you, that's it, of the total true positives that we want. So next line down we go, okay, this one we were a little bit less confident, but turns out that one was also actually a conversion. So now we've got 2 1s and 0 zeros. So we've got 2 true positives. That chart does not match up. Actually, I've got a.
How does it match up?
Let me grab the code. So this right here is an ideal model in the Excel spreadsheet. It basically predicts everything correctly. Oh, here it is. So this is where all the ones are going to be on top and all the zeros are going to be on bottom. So I'll copy that line and have that generated for you. But I wanted to give the squiggle one first just so you know what it can end up looking like. So there we go. No? Oh, I think I've got all the same probabilities in there. All right, let me go back here. Live demo. Yeah. Okay, so I think we had 3 in the spreadsheet versus 4. That's what I want to see. Okay, perfect. And let's go back to here and hover over here. Okay, so I think you get the gist. Basically, if we have a true positive at our cut point, we draw the line up. If we have false positive, we draw the line right. Or basically, as we encounter 1s, we draw the line up. As we encounter 0s, we draw the line to the right, assuming everything is in the order of prediction confidence. So I can show one other caveat to that is if you have 2 probabilities that have the same value, you will get a diagonal line. So it takes those both into account at the same time because they had the same ranking in terms of probability order. So there's also one summary statistic we can get from this, a single number that kind of encapsulates the overall effectiveness of the predictability of the model, and that is the area underneath the curve. Anything above 0.5 is good, anything below 0.5 is bad. But that is one way to test the models that we generate and see how good they are at actually predicting what the outcome is going to be.
So metrics are very important, and these are standard metrics that everybody uses around the world. We also have in-house metrics that we also embrace for evaluation purposes. So when it comes to data science, data is king. And this is a curve here that Banco and Brill from Microsoft came up with a few years ago. And I guess the question is, would you prefer to have more data, or would you prefer to have more data scientists? Can we have a show of hands? More data? More data scientists? Wow, we're split down the middle here. And the correct answer is? Data. Data is king. And at W3I in NativeX, we got tons of data. And we have a lot of science going on as well. And this curve here, they correspond to saying, well, on the x-axis, we have the size of training corpus. And on the y-axis, we have a metric, let's say accuracy. And what it shows is that there's a whole bunch of modeling algorithms here, and they all improve as you add more and more data. Now, you would not see this kind of lift by adding more features or more feature engineering. But by throwing more data at the problem, you're getting better estimates. And I think that's the bottom line for this graph here. So having said that, let's segue to Esse, who comes from a business analytics perspective, and he's the king of data at W3I.
Thanks, Jimmy. So we've already told you that we have a ton of data, and then we've also shown what a perfect model looks like and then what a bad model looks like. Now I'm going to talk about our experience when we started working with generating these models and the problems we encountered when we started with this project. So when we started using our data warehouse, internal data warehouse, for modeling for generating these models. And what we found out was sometimes we were not tracking the right data. Sometimes the team did not really understand what the data exactly meant. And of course, sometimes we had bugs too. So these were the problems that we ran into. So we had to really spend time figuring out what's going on, really understanding is what we're tracking really happening, is that what's happening in the device? So we really had to figure that out before we started getting better models. Also, the fact that we had a very cross-functional team with experience with data science, engineering, BI, helped us a lot figure out and really understand what's happening. So if you're really thinking about doing a data science project, these are some of the questions that you should be asking. Are we really tracking the right data? Is what we're tracking really what's happening in the real world? And also, does the team really understand what's happening? And of course, don't assume your data is right. You always have to make sure your data is correct and you don't have bugs anywhere, because if your data does not really reflect what's happening in the real world, then your model is not going to be as good. So you'll spend more time fixing that later. So the faster you get it right, the better. So that's one experience. Also, for training our models, when we started using the data warehouse, what we found out was, so these are like two sets of two different problems from engineering perspective. So from the BI side, business intelligence side, emphasis is on answering questions based on how much, how many, etc., which is really aggregated. Versus in the data science world, we're really interested in knowing, okay, this event resulted in this event, etc. So it's more like disparate, distinct events happening, and we want to know what's really happened. So as we started working with our data science projects, we started using the data warehouse, and what we found out was we were spending a lot of time trying to undo the aggregation and trying to really lay out the data in the format that the R code that Brett was showing you could use. So we decided to have a separate database to really host our training data. Another reason was because we want to try out a lot of things, move fast, that was not possible if you're like doing it in a large data warehouse, because that affects the whole organization, versus separating ourselves gave us the ability to add features continuously. So these are some of our experiences.
Okay. So data science is not all about experimentation. It's really about the infrastructure, the data warehouses, being able to push back on infrastructure to build features and deploy models into production. And so Joe is going to tell us a little bit about his experiences with supporting the team from an infrastructure perspective.
So one challenge we ran into once we implemented some Bayesian models, and we had these huge sets of probabilities collected, and we need to be able to access lots of them in real time. So this isn't really, we're still in the early stages. We haven't necessarily found the perfect solution for this yet. But some of the things we've done so far are we use Cassandra for storage. It's an open source distributed NoSQL database management system. We were already using it for other purposes, and it's great at handling large numbers of requests with good scalability. Actually, a couple coworkers of ours are doing a session called Scaling with Cassandra at 3:40 if you want to hear more about that. So one question we had right away was, we've got all these probabilities, and we need to know, find the best way to access them quickly. And one approach would be to just store all the probabilities individually, and then just fetch them all, and then sort them. This is really great for the models because it lets them be maximally flexible and segment the world however they like, each differently. And then another approach that we've talked about is rather to pre-sort the offers for each bucket so that we can just fetch them for each scenario, just one fetch per scenario. And this is much more performant, but it really limits our models because they have to segment the world in the same way or a similar way. So like I said, we haven't really solved that question yet, but we are considering hybrids of the two approaches, and we're kind of evaluating the performance of both. Another question with this was how much caching to do. Again, with like a huge amount of data, it's too much data to cache in its entirety. So, and also Cassandra is sort of like a giant distributed cache. But we still wanted the data to be available in memory whenever possible for the best performance. Again, here we're still evaluating it, but what we've done so far is we've just created settings so that we can turn this caching on and off for various feature sets, and then also to just tune it to different levels. That's kind of one of the points I wanted to mention a little bit later. But so moving on, it's really important to be able to evaluate your results and see how you're doing from the beginning. So one step we took was to automate our data extraction and model building and other steps from the beginning. And we think this really pays off because that way what you have is a repeatable system. You don't have to worry about manual errors impacting your results, and you can just run it, and it really saves you time as you end up doing these things over and over again. We also found it really valuable to have tons of configuration options built in so that you can easily tune your behavior without having to redeploy it. A good example of this is we have a setting to control what % of our traffic is going to our various sorting algorithms. So we can easily, we come up with a new algorithm or a new model, and we can just roll it out to 1% of our traffic. And then if it looks good, we can gradually improve it or increase the amount of traffic and look at the results and evaluate the performance. And then we also think that A/B testing is really important, so we can have a rigorous way of measuring our results in terms of the revenue impact. So we have an experimentation framework that lets us set up experiments for different segments of traffic. And then what we do is we can partition the traffic into 2 control groups and an experimental treatment group. This lets us look at how much variability there is intrinsic in the system when we're comparing our different approaches. And so we found that to be pretty important as well. And then aside from evaluating the business results, we also think it's really important, like Jimmy said, to monitor everything. So now I'm talking about monitoring in terms of what logic is actually firing and how is the code actually performing. This is really useful, of course, for any application, but especially when you're developing really quickly, building new architecture and using new tools, it's especially important so you can really see why things are happening the way they are and why you're getting the results that you are. We were already using a tool called StatsD quite a bit. It's an open source module that Etsy developed. It's really simple. You just send it event data. You send it, the occurrence of an event or the duration of an event. It uses UDP, so there's minimal overhead, and if it goes down, your app is fine. And it also has built-in sampling, so you can use it even for very high-frequency events and just set the sampling to 1 in 1,000 or something like that. And what StatsD does is it passes the data on to Graphite, which is this flexible graphing tool, and then from there we can take the data and do all kinds of things with it. I know you can't really see these graphs, what they're actually showing, but they're pretty, so I thought I'd put them in there. So we collect metrics. We use counters mainly for functional behaviors, and then we have timers around the code segments we're interested in. And we found this really helpful as we're rolling things out, and making sure the internal behavior is what we expect it to be, and getting insight on which code paths are being hit, and collecting performance information. So that's what I had.
All right, thanks, Joe. All right, I guess we also are concerned about infrastructure, and there are a number of colos around the country and around the world that are being used by NativeX. But in addition, we've been working on AWS because it gives us enhanced flexibility and also a lot of computational effort. So we found that to be very useful to do experimentation. So naturally enough, today we're just talking about our engineering effort and some of our initial projects that we've rolled out. In addition, going forward and currently, we're being very ambitious in building out additional functionality to segment the user base, consumer base, the world of ads and the world of publishers. And we're also experimenting with large data systems like Hadoop, Redshift, and Spark. And just to give you an idea of what's involved, this is a user experience from an advertiser's perspective. And let's say I'm an advertiser, and I want to, I'm prepared to pay so much per click. Let's say, in this case here, 73 cents. I want to see what kind of audience I can reach by bidding 73 cents. And here what we have is a forecasting tool. So by bidding 73 cents for, in the context of, say, these keywords here, I can expect to get about 100 clicks. Now, if I change this bid here, I can get more or less clicks. Now, this is a very simple user experience from an advertiser's perspective, but the amount of engineering and data science behind this is amazing. So first of all, you need to forecast the number of impressions in each segment of your world. In addition to that, you need to forecast how many clicks. And then also, that's for later. We're saving the best for last. So there's a lot of prediction and forecasting and modeling that goes in here to make this dial available to an advertiser. And these are some of the things that we're trying to build out currently. So I guess we've got a question for the audience. We started off by asking the question about data science and, was it opportunity plus instinct equals profit, as Quark would say? Or do we need to have more precise calculations, otherwise we crash and burn? And so I think we're in the Han Solo camp, and we're looking to hire some Han Solos. So I'm not sure if there are any Han Solos in the audience today. Can we have a show of hands, please? Han Solos? Any quarks? Okay. Anyway, I guess we want to stop there and leave some time for questions or comments. Thank you very much for your attention. Questions?
I had a question for that guy.
Okay.
So the advertisement. So you get an ad, and it's shown up one time, and it was conversion. Do you include that? I mean, because right now it's got 100% conversion.
Yes, we have a process called smoothing, where we recognize that not every segment, not every combination of advertising publishers is going to have a lot of data to it. So what we do is we take a global model, and we say, let's take a little bit of this one where we have very specific information, and a little bit of this one where we have a lot of information, and kind of blend them together. That also helps us there are filters before we even start modeling. It says we need to achieve a certain number of times.
It's got to be shown maybe 100 times before we consider it big enough for weight.
Yeah, so one that has almost no views would just be, its weighting would be vanishingly small against the global that it's smoothed to.
At the same time, we do need to rank it against other offers, so we give it a global, like, knowing as much as we know about this ad, here's what the problem is.
So we've got a Bayesian hierarchical model going on here. We're saying we have prior information. We assume the background network averages are the priors, and then we've got this local model, which is more the information from this offer or ad, and we combine those in a Bayesian way. So we do Bayesian updating. Question in the back?
Yeah, you have a lot of internal data from your clicks and whatnot. What external data do you use?
Well, that's a good question. So there are lots of third-party data sources out there. I don't think we can comment on what we're using currently. But so, for example, one could think of using Nielsen audience type data to understand various demographics within zip code areas. But I don't want to comment on that right now. But we are using various third-party data. And okay, sorry.
You spoke a little bit about experimenting within your client environment.
Yeah.
I'm just kind of curious how you're able to do that contractually and how that flies, because it's usually tough to get anyone in the business to agree to experiment with something that really affects revenue.
Sure. I think it's a great question. So just for the audience, so how do we get away with doing experimentation in a live world? And it's a great question. And so as I said earlier, all the way from the CEO down, there's a belief in data science can improve the profitability of advertisers, publishers, and user experience. So naturally, we actually run a small percentage of our traffic in random mode. We need to see how good our system is doing versus a random setting. And this provides feedback on how well our system is doing. In addition, it provides us the ability to learn about things we didn't know already. If we just kept serving offers and ads based upon what we know, we would be entirely in exploit mode. We need to learn and get into explore mode as well. And so this random process helps us get into explore mode. In addition to doing this random serving or ranking, we do this experimentation. And so experimentation hopefully leads to positive results, but it also leads us to learn more about the different offers or ads and consumers.
And we've also been working with our sales department to kind of help them explain the benefits to the advertisers.
So
the advertisers have that built in.
Sure. I mean, this is par for the course in ad serving across the digital spectrum, I guess.
Usually we're experimenting with something where we have at least a reasonable expectation that it will actually be better for the advertiser. So.
You got a question? Yeah.
What other kinds of math besides statistics are you guys using?
So what other kind of math that we're using? So we're using regression models. So we have binomial logistic regression models. We also have decision trees and ensembles of decision trees. And then, so we're also looking at supervised learning, machine learning, where you know that this event is a conversion or not a conversion. And we're also using clustering, unsupervised learning, to segment the world of consumers or the world of ads. So does that answer your question?
Yeah.
So we're using a lot of different techniques. All right, I think we're being kicked out here. So thank you very much again.
We can probably meet